Hello, I'm back, and I've decided today to cover how Rust's borrow checker works and how lifetimes work in Rust. So we're going to start with how data types are stored in general. And one of the really important things I wanted to cover is the difference between the heap and the stack. So when you're working with your computer, there are different areas of memory you can store things in. Now, numbers, just simple numbers, are always the same size. And if you make this right here, x is equal to 5, Rust is going to store that on something called the stack, which is basically just memory that it moves up and down through. It kind of seeks through it really quickly, and it's kind of like its little scratch pad that it uses for smaller values. But if you want to make something larger that may need to grow over time or have an undetermined size, then you're going to make it a heap type. Like, for example, vectors are a heap type. They're stored on the heap because they cannot fit on the stack. And based on that, I wanted to go over some of how ownership and things work in Rust. So if we were to declare a string, doesn't need to be mutable, string here, let's make it say hello. We've created a string right here, and it owns it right here. So what that means is this function right here, and specifically this variable, owns this specific value we've created here. Now, as soon as this function exits, nothing else outside of this function is ever going to reference this string. So that means that the string goes out of scope, it's called, and the compiler knows that it can clean up any memory that was used to store that value. Now, another thing is you can transfer ownership. So right now you can see we can print x. And if we print x here, it just says hello. But if we were to transfer ownership of x to this variable y, you can see that Rust gives us an error because we're trying to use the value that was in x, but we've moved the value to y. So now y owns it, and x is no longer a valid thing. X doesn't contain any valid data, and we can't work with it for any more time. So one of the things you can do here is clone the value, because the problem is here that a string is a heap type, meaning that it can't be moved around really easily like something on the stack can. So it can actually take a decent bit of extra memory to make another copy of a heap type. So Rust, instead of just doing that automatically, is actually going to make us explicitly tell it to clone the value. And if we tell it to clone the value, that means make another copy. Now y has its own independent copy of the data, x never lost anything, and we can print x right here as we did before. Another thing that I wanted to cover was borrowing. So let's just create a simple value here, x equals, wait, no. Another thing I wanted to cover was stack types. So as you heard me saying earlier, stack types are really easy to move around. And if we create one here that is a number is a stack type, always. It is very easy to work with inside of your computer. The computer can move it around really well because it's a really tiny piece of data. And so it can sit right on the stack. And what that means is if I create y here, and I set it to the value of x, and then I try to print x here, the compiler doesn't care because it automatically moves this value, because moving the value here is basically the same as if we just left it in x. Like the performance cost is so low that Rust doesn't care and it just moves it. So it's just making a copy of it, and there's a specific thing for it. If you haven't learned yet, Rust has traits, which basically tell the language what you can do with certain things, and there is a trait for copy, which tells it that you can copy a value, and there's also one for clone. So this helps you distinguish between how the types are worked with. You can still have a type stored on the heap that is copy if you really want to, but most likely it will be copying a piece of information on where that data is on the heap, or it'll make a clone anyway and then share that data. So it's not really recommended to define types that are on the heap as copy because it just causes problems. Next thing I wanted to cover is borrowing. So if I'm to create a value here, let's make it x again. We're going to make x string with the value of hello. Then I can create a reference here. So for example, I'm going to make that variable name n, and let's quickly go up here and create a function called length. Now length is going to take in that value as a reference and return an integer. So what it is doing here is, normally if you're to give the value to something else, it would just take it. It wouldn't let you use it afterwards. But when you use a reference, you're telling something, hey, you can look at this for a bit of time. I'm going to lend this value to you for a bit, and I'm not going to do anything to that value while you're looking at it. And that allows you to let something else look at it without losing ownership of it. So x still owns this value, but this length function here is acknowledging that x owns it and it's temporarily using it. So now if we print here, let's just use this, you can see that x is valid and the number returned from n is valid because we never lost the value of x. We never transferred the ownership. And another thing about these so-called immutable borrows, meaning that they are borrows, this function is borrowing the value and it has made a promise to never modify that value. So let's create borrow1 here as @x and borrow2 here as @x, and we can print both of them right here. They can both coexist at the same time because the compiler knows that x is never going to change during this time period. You cannot change x right now. It knows this. So it knows that while these two values exist, it knows that no matter how many times you read them, the value isn't going to randomly change. And it allows you to do this, so I can have two references to the same value here. Now, where this gets a little more confusing is with mutable borrows. So let's clean this up really quick, and I will show you. So if we create a mutable x equals string, let's make it our hello value again. No, IntelliSense, give me the lowercase hello, because I like it. I don't want it to think that it's formal. I am going to create a borrow here that is a mutable reference to x. And what that means is that x is guaranteeing to you from now on until this borrow is no longer used, and it is guaranteed that it will no longer be used, that x will not change unless b changes it. So b currently, you can think of it as when you create an immutable borrow, you're letting people look at the object that you have. They can look at it as much as they want, but they can't touch it. Whereas if you use b, as in the case of b here, where we are mutably borrowing it, you're saying you and only you can touch this object. Nobody else gets to touch it, and it is going to stay exactly how you leave it until you give up that object. So now, if I was to push this string onto it, I'm adding world at the end of x here, because this is a reference. So you got to remember that while I'm using b here, it's all referring back to this one value here. So as soon as b no longer exists, it is going to just mean x. All of this is the same value. So now if I'm to print b, you can see that I've made a modification to the original value, which you can't do with an immutable reference. Another thing you have to think about though with mutable references is that you can't have two of them at once because it is guaranteeing that there can only be one at a time. You can't have anything else messing around with it because otherwise it makes it inconsistent. So right here, if I change this up, you can see that it's complaining because you can't borrow it as mutable more than once at a time, because the compiler can't guarantee that the value won't be changed. The reason it doesn't care when this isn't here is because Rust looks at this and it says I know that neither of these values will be touched and they're going to go out of scope without being used. So when the Rust compiler is looking at this, it effectively translates down to this, and then it effectively translates down to this. So it actually does nothing unless I make that print call here, because it's really smart. It knows when it can save time and space. Another thing you need to know is that you can't have any immutable value borrows at the same time as a mutable one, because if you think about it, let's say B1 wants to look at this value. It wants to keep looking at this value, and B2 wants to do some modifications. So in the middle of B1 looking at the value, B2 could change it, and all of a sudden you have no idea what's going on. B1 could be halfway through reading, let's say, some very important financial records, because we're storing those in strings, yeah. Let's say some very important financial records, and suddenly B2 updates it, and now B1's really confused because it doesn't know what's going on. It was seeing completely different data before. And that causes problems, so Rust says you can't do that. One more thing that needs to be covered is lifetimes. As I was mentioning earlier, things go out of scope. We will show this right here. I'm going to make a value x is equal to 5. And I'm going to set that r that I created but did not initialize here to a reference to x. And now if I try and print r, there's a problem, because you can see that Rust has created this value here. X owns the value, and we're trying to tell r that it can have a look at that value. But when you hit right here in the code, X no longer exists. Rust has decided that this value can go away, but r still needs that value. It still needs to keep looking at it. So Rust doesn't let you do this, because you're trying to tell Rust to look at a value that's going to disappear halfway through the existence of its borrow. And another thing that's really annoying in Rust that a lot of people will struggle with is lifetimes. So I'm going to create a function longest, and I'm going to give it a lifetime parameter here. Actually, no, I'll show you that in a second. And we're going to create string 1, which is an @stir. It's a reference to a stir. That's a weird Rust syntax for referencing a string. And we're going to create y, which will also be a reference to a string. And we're going to output the string that is the longest. So we're going to return whichever string is longest. And you can already see that Rust is having problems here, because it's looking at this function and it's saying, hold on just 1 second. I'm not really seeing anything yet that indicates that this value is going to live long enough for whatever's using it. So it wants me to tell it how long that value is going to live. And to do this in Rust, we use lifetime parameters, which are basically a guarantee that a value will live a certain amount of time. So we're going to say that when you call longest, you are passing in a lifetime, which is the amount of time that a thing must live for. And we're going to say this value will live for at least that amount of time, this value will live for at least that amount of time, and the returned value will live for at least that amount of time. And now Rust sees this and it knows, okay, when you pass in these two things, this is going to live for that amount of time. And it won't let you write code that doesn't guarantee that unless you use unsafe programming, but that's a whole can of worms. You don't really want to do that in Rust. And what we're telling it now is exactly as I said. We're telling it that this value will live for that amount of time. So now I can compare the values. So I'm going to say if the length of the string x is greater than y, then we're going to return x. Otherwise, we return y. And now this is going to return whichever of the two strings is longest. And now we just create a string here. Let's create s1, string from hello, and then we're going to create our result here. And then we're going to create string 2, and we're going to create result, and the result is going to be the return type, or the return from that value of longest here. And then we can print result here. And the reason we can print result within this function, or within this scope right here, these braces, it's called a scope, is because Rust knows that all of these values, string 2 and string 1, will live for let me actually this code pattern is wrong, sorry. Just to make it more clear, that does do exactly the same thing, but this makes it more clear. These are references to those values. And string 1 here is going to live for the entire function, but string 2 goes away as soon as this ends. So it's fine in here because string 2 still exists, but let's say if I try and print result here, there's a problem. Because we're passing in string 2, and Rust is saying that result must live up to here. But string 2, which Rust knows that must live as long as result lives, isn't going to live for that long. It's going to go away here. So Rust stops you right here when you try and print it here, because it knows that that's simply not possible. It will not live for that long. And that's really the basics of how lifetimes work. Just a quick recap. Rust keeps data on the stack, which is for quick access, and the heap, which is more for larger types that are stored in larger areas of memory. Only one thing can own a value at a time, but multiple things can look at it at a time. Only one thing can change a value at a time, and if something's changing that value, then nothing else can look at the value. And whenever you create a reference to a value, whether it wants to be able to change it or just look at it, you must ensure that the value itself lives as long as that reference. Thank you for watching my video. If you enjoy, please subscribe. I would also appreciate if you watch some of my other ones. I've made some pretty cool projects, and I will hopefully see you in another video where I will cover more programming concepts.